Hello, and welcome to On Consciousness with Bernie Baars. My name is David Edelman. I'm a neuroscientist, but I came to that particular profession through a weird sort of multifaceted trajectory. I started off actually as a human paleontologist. I got my PhD in paleoanthropology. I studied the evolution of bipedal locomotion, of walking on two legs. And for some strange reason, I found myself some years later after my PhD in a postdoc studying gene transcriptional regulation, after which I moved on to cellular neurobiology and curiously took this odd turn, which will kind of be part of the riff that we go off on today, which is consciousness, the nature of consciousness. And in fact, I met Bernie Baars at the Neurosciences Institute sometime shortly before 2005. And Bernie and I started discussing the nature of consciousness, and in particular, consciousness in non-human animals. And from there, I've been smitten. And I've moved on, and I'm particularly interested in the nature of consciousness in non-human animals who can't communicate with us, at least verbally. Behaviorally, we can argue that they're capable of doing just that. Somehow, I found myself enamored of cephalopods, in particular, the octopus. And the reason I got into octopuses was that I had asked myself a question, which was definitely inspired by my discussions with Bernie and with Anil Seth, now at the University of Sussex, about animal consciousness. And I wondered how far we could go. Who among all of the non-human animals was a member of the Consciousness Club, the C Club? And so I started reading about these amazing animals, the cephalopods, and in particular octopuses, and I realized, wow, these are absolutely incredible animals behaviorally, and they actually have really, really big brains. And the most extraordinary thing to me initially at that point was the fact that the largest brain among invertebrates, the brain that comes closest to the octopus brain in size, is the brain of a honeybee, and that is 1/300th the size of typical octopus brain, the common octopus brain, with 500 million neurons, about 300 million in the arms, and another 200 million between the eyes and what we would think of as the head, but is really called the mantle. In any case, here I sit. I've become a devotee of the nature of consciousness, and that brings us to today. So I am joined by, of course, Bernie Baars and Ernie Krichmar, who is a neuroscientist and roboticist who has been at UC Irvine for some years. And Jeff and I, actually came to know each other from our work at the Neurosciences Institute. So Jeff, why don't you tell me who you are, what you're about, and what you've been doing these past years?
Sure. Thanks, David. And like you, I didn't come at this from a direct path. I started as a computer scientist, worked at companies, Raytheon Corporation, IBM, doing real-time and embedded systems. And then at some point, I went back to school and got very interested in how the brain works and wanted to put these things together. And then with that background and that interest, I ran across what was going on at the Neuroscience Institute in the late 90s. And they were doing real-time embedded systems with these brain-based devices and having artificial brains actually guiding or controlling or, I don't know, being these devices. And I thought, how cool is that? So
Super cool.
Wasn't a hard move to go from, DC area to La Jolla.
Oh, no.
But yeah, it was fantastic. So I was there about 10 years, and then I started my own lab doing this very similar work at UC Irvine around 2008. And I've been there ever since, and we're still walking the walk, talking the talk.
Excellent. Wow, time flies.
I know.
So, yeah, I find, Jeff, I find your trajectory, and I think Bernie would agree, particularly interesting because as we had sort of discussed informally before, when you started doing all of this stuff, this is all really, really new. And this notion of essentially putting biology, the biology of the brain first and foremost in neural modeling, and the idea of modeling in a machine the complexities, the details of nervous systems and their function, that was really, really new when you started, wasn't it?
It was. We were about the only group out there doing this. And I remember when I started going to conferences and talking about the work, that we would be the only ones doing that, but everyone was fascinated by it. And one of the things, because we were trying to build brains, and brains have lots of complexity, and they're big. People were asking, why are your artificial brains so big and complicated? I go, because that's the real thing. So it was this weird thing. And then you come today, and they're all talking about, these huge, deep neural networks. So it's come full circle where the rest of the field has now realized, to solve interesting problems, you have to have enough neural power, and you have to have enough complexity.
Right. So Bernie, what do you think about this particular line of work?
It's almost intimidating how rapidly it's growing in the right direction. When and whether it will get to conscious brains, I choose not to know about, but it's possible. And I should mention that the word consciousness, about the time when I got my PhD, was taboo. You were not supposed to pronounce that word, and I think I may have lost my first job because I mentioned the word consciousness too often. I wouldn't shut up.
So, wow, what you're saying basically is that if this had been, say 40 years ago, if Jeff and I had spouted this stuff, we would have been essentially burnt at the stake by Giordano Bruno or something.
Yes, exactly.
We were
That's a
heretics.
very good example, actually, because Bruno was violating the Vatican's rules about whatever it was.
Yeah.
And so they decided to burn him and be done with all that nonsense. So it was very effective in warning everybody else to shut up,
Right.
including, I think, Copernicus.
Yeah, absolutely.
Because Copernicus, as I understand it, actually never published the book that's attributed to him.
Oh, that's interesting.
He waited to die first.
Well, that's one way to become famous.
Oh, absolutely,
without
yes.
all of the detritus, right? Just get it out of the way.
Yes,
But no royalties.
No royalties.
No
That's
royalties.
the downside. But in any case, I mean, it's really, really interesting, isn't it, how things have sort of turned. They haven't exactly turned on a dime because, again, we're talking about 4 or 5 decades worth of history. And so now here we are, and consciousness is not really taboo, although I think if you sort of brandish that word at 50% of your typical neuroscientists, their reaction might be a roll of the eyes.
Yes.
Maybe, not necessarily because they don't believe it's there, but they might question, well, how do you study this thing? How do you study this process, actually,
Right.
I should say. And the rest of them would be, well, you guys can't even define it, so why are you wasting our time? And that is a big issue. And the one interesting thing, and I'll just put this foursquare in front of us so that we can kind of unpack it as we go on explicitly or implicitly later, the idea that, you need to start with this hard and fast definition, and that may well be true. Definitions are really useful in science, obviously. They're good because they set people down very specific paths, and perhaps you could argue you waste less time. But when it comes to consciousness, we do very much have observable correlates and properties. We can see in animals that are conscious, and you and I, Bernie, have talked about this, and I guess to some extent, Jeff, you and I may have talked about this before, but if you look at waking versus sleep states, in particular deep sleep, non-REM sleep, slow wave sleep involving delta waves, et cetera, well, you have two very, very sort of diametrically opposed conditions in the brain, phases in the brain. And arguably, one is a phase in which conscious processing is going on, and the other is a phase in which it disappears. And lo and behold, there are certain properties and correlates that are there when you're putatively aware and awake, and they simply go away when you're in a deep, dreamless sleep or you're in a coma. That's really amazing. And that speaks to the fact that we're actually studying a real process, I think. And we have something to build on.
Yeah, except if you're talking about to a roboticist like myself, it gets tricky Because how will I convince you that my robot is conscious, even if it had all those properties? I know you guys are conscious because I kind of can put myself in your shoes and know that you're probably having the same feelings that I am. But with a robot or a machine, it's more difficult. Then it also begs the question, like, why would you make a conscious machine? Maybe to study it, but is there any benefit to having a conscious machine?
Right. So let me ask you this. Just sort of, it's not exactly a devil's advocate position, but it's the position of I'm putting myself in the position of a skeptic that might approach this and query you about it. So vis-a-vis machines and the idea of potentially engendering conscious processing in a machine, would you not say? I mean, to a skeptic's eye, would it not be sufficient to sort of offer that, oh, wow, we didn't program these particular things in, and yet you can see sort of these sort of functional equivalents of sort of waveforms or propagation events taking place in the simulated brain that mirabile dictu look like the real deal, but we didn't program them in, but we were after simulating the same sorts of conditions that you might observe, if you were studying a conscious animal. Would that not be very, very potent sort of evidence for that possibility?
You're being very ambitious.
Of course I am.
I'm much more cautious and step by step. I think people are conscious. I think you both are conscious. I think I'm conscious, and so on. And I think we can prove that in a variety of ways. I wouldn't even dare to look at computers and wonder, because computers don't have evolution, they don't have development, they don't have nervous systems.
But we can simulate those things. So then, is it the same thing? That's an open question.
Well,
That's a very open question.
My objection to the simulation argument is that simulating something is not creating it. And that used to be a very clear distinction, and it's becoming less and less clear as the computational world evolves into these very lifelike, very brain-like systems, networks.
Yeah, no,
and
I
that's
agree.
a tricky question right now, but it used to be, in the old days, you used to say, the map is not the territory. Right? And we're working on the map, and we're doing our best, and don't step off the map and expect to survive.
Well, let me counter, or at least try to propose some sort of counter arguments, right? The first counter, it's not necessarily a counter, but it sort of speaks to the real value of Jeff's work over well more than 20 years, which is that, speaking of increments, you mentioned increments and incremental. In a certain sense, Jeff, ever since he arrived at the Neurosciences Institute, and in his mind's eye probably before that, he's been taking sort of an incremental approach to all of this, and he's been going through step by step and essentially going after what I would argue are the multiple sine qua non of conscious processing. So in other words, memory. We talked about this before. So memory is important, I would argue, and some people would agree with me. Others, perhaps like Christoph Koch, I don't know, might disagree with me. But memory, I believe, in some form or shape is absolutely pivotal to consciousness. You have to have some form of memory, and the definition of memory may be very Catholic in terms of the time point, the temporality of it. The idea that if you can hold a representation in your head together for 200 milliseconds, even just 200 milliseconds or a second, it effectively counts as memory as long as you can sort of act on that in some effective way.
Sure.
Well, let me take a step back. So you made a point, like we've been going, step by step from the Neuroscience Institute, testing different things. And I kind of am not always comfortable using the C word.
Right.
Maybe the other C word, cognition. But the power that we've had is, if we look at a memory system like you were talking about, and we have been able to successfully build an artificial brain that shows characteristics of memory. The nice thing about it from a science point of view is we built the the artificial brain, so we have access to every component of it.
Yes.
And so that's allowed us to really, in a way that neuroscientists and experimentalists cannot do, is just pick it apart and figure out why it's working like it does. And there's enough data out there that we can compare the emergent behavior of this artificial brain. It is acting a little bit, like Bernie said, it's acting a little bit like a real brain. But now we have access to more than a bench neuroscientist did.
Absolutely.
I think that's a really powerful tool. And maybe the better way of looking at this, maybe this is a powerful tool to look at the elements that lead to cognition and I guess the other C word, consciousness.
Yeah. So let me speak to the second counter that I had mentioned, that I had two counters to your proposition that, simulations are sort of, they're kind of iffy territory. So my second counter relates to just this sort of thing. And the second counter is that, well, we're advancing pretty damn, not necessarily rapidly, but we're making real strides in terms of, even in hardware, we're starting to emulate the organization of even to the point of emulating individual neurons, the way they look, the way they would behave, actually. Sort of these sort of gated sort of entities that, they have threshold gates. They might be jazzed by something that is essentially a simulation of serotonin versus dopamine. And they do all the things. We're headed very much, I do believe, and maybe I'm overly optimistic, I do believe we're headed to a point where we're getting pretty good at that. Now, the hardware in silico or in gallium arsenide or whatever you choose to use as your substrate, we're getting to the point where you can look at the actual entity on the silicon plate, and you can say, wow, structurally, God, you guys have made hay. This is kind of starting to look like that you wish to emulate. And then functionally, right? We're starting to know as neuroscientists the rules of the game, right? We know an awful lot about excitation, about inhibition. We don't know the world about it, but we know an awful lot. We know about essentially visual fields, how fields are defined, in and across the nervous system for different areas of vision, areas of auditory areas, et cetera, et cetera. I think we're doing a pretty good job of starting to get that stuff into these, what you might call at some point simulations.
Yeah,
but
there's actually hardware coming off. It's interesting you said that about the computers. There's people building hardware that realize that there's something called Moore's Law that we've hit the wall against. We can't make our computers any faster. So they turn to the brain. And they were looking at building neural elements because it's one of the interesting things is how efficient brains are,
right,
how efficient biology is. So coming from a completely different reason, we just have to make better computers that take less energy.
Exactly.
So they actually they're making these systems. Some of the big manufacturers like IBM and Intel are making systems that have neurons, that have synapses,
right,
that run at extremely low power, and that can do more things than a current computer can.
Right. So
I hopped on that really early because I said, oh, this is the perfect embedded processor for an artificial brain, for a brain-based device. Right. So I've been following this and working with them closely, but it's kind of fascinating to me that they are not neuroscientists by any means, but they realized some of the things that brains do so efficiently that we should mimic. Yeah.
And this is interesting because this goes back to a real important touchstone for me as somebody who fancies himself, at least in my mind's eye, maybe I'm overly egotistical, I fancy myself an evolutionist, a dyed-in-the-wool evolutionist. And as an evolutionist, I always consider various problems that animals solve in different ways, cognitively, physically, biomechanically. I sort of reduce them in a certain way from the outside in. I start from the outside and I say, well, what happens when you see stuff? If you're starting from the eye and you're starting from the surface of the retina, even before that, you're dealing with the physics of light. You're dealing with some very, very hard and fast general principles of the physical world, right? And it should be no surprise to anybody that even engineers who are trying to, emulate nervous systems and what nervous systems do, they're hitting on some very sort of central kinds of points that evolutionists have always sort of thought about. This has been very important. And it's not an accident because the physical world allows only certain kinds of solutions. That is, if you're operating from the outside in. Now, that's really intriguing because I think that suggests there's a great deal of hope. I may be, an over-the-top optimist about this, but Jeff pointed out something really, really interesting, which is the notion of energy use. And that goes back to something very, very basic in physics, and it has affected computer science for many years, which is the problem of heat and heat dissipation, and the efficiency of systems and how much, excuse the expression, how much light versus how much heat you produce, right? And heat has always been a huge issue. And as we miniaturized in microcircuitry, of course, it becomes a cardinal issue. And you see in supercomputers, you see massive efforts made to cool these.
This is one of my pet projects. I've been talking to other people about this, just how you save energy with looking at biological tricks. And there's many of them. It's not just the brain, too. It's also the body. The body is doing all sorts of interesting, what we like to call morphological computation, where it's exploiting the environment. So when we walk, we're exploiting gravity and friction. Right. When fish that swim really fast, they actually are able to generate more thrust than they put out because they cause turbulence behind them. That gives them an extra boost of thrust. Right. Insects do this.
Absolutely.
So there's all these tricks, and I think we're going to have to do this, especially with, I hate to say it, climate change, and also the way artificial intelligence and data science is going, that we have these huge data farms. We have to do things much more efficiently.
Absolutely.
So I think turning to biology, brain and just basic biology is definitely a key to that.
And channeling my inner optimist, and Bernie, you should sort of, check me on this if I'm going too far afield.
You're way too optimistic.
I'm always an optimist,
Oh, Bernie, when did you become such a pessimist?
I talk a tough game, but, I'm a pushover. I'm a total optimist. Yeah. So here's the thing. My inner optimist tells me that, in effect, not to put too much conceit on this, but we've gathered a lot of information as neuroscientists. We've got a lot of information about neurobiology under our belt. We've by no means arrived, right? But we've really got a lot of stuff. And the most heartening thing for me to hear when Jeff speaks about this is the fact that now they're really considering what turn out to be some very, very fundamental engineering problems to solve, which implies that I don't see the barriers anymore to really intelligent machines and putatively perhaps conscious machines in the future. I no longer see the barriers as necessarily in our way being neurobiological in principle, right? Even though there are some. I see the major barriers in terms of miniaturization related to dissipating heat and energy efficiency, and the fact that brains run on such low energy, as you said. I mean, they're super efficient, and we don't have machines that rival that yet, but we're certainly on the path. But these are solvable. These are soluble, I think, over the long haul. So, yeah. What do you think?
So I can make the opposite case.
Okay, go for it.
And just for the hell of it, one of the things that's astonishing, I think, about the human brain in particular, just because we know a lot about the human brain, and there are comparable brains, of course, in size relative to the bodies, whales, elephants, and you're telling me the bees are...
well, they have big brains for their size. They don't have big brains in any absolute sense.
But
a million neurons is
a million neurons. They do amazing.
A million neurons
amazing
is
absolutely.
Yeah.
It's my late dad would say it's combinatorial. It's one of his favorite words.
It is what?
Combinatorial.
Combinatorial.
Yeah,
yes.
It just sort of explodes after a certain.
Yes, exactly.
Yeah.
And what baffles me about the human brain is how expensive it is and how risky it is and how it makes, we've got this big brain right on top of our vertical bodies.
Right.
And the moment we rise above the horizon, walking up a hill, somebody's going to take aim at you and throw a rock in your...
Yeah, where you live.
Rough part of town, right? Wow, I would want to live in your neighborhood. Wow. But but you've just, oh my gosh, you've just jazzed my inner paleoanthropologist. You've
Good.
taken me back. You've unleashed the beast.
Yes.
Now I've got to respond. So here's the thing. What's really intriguing is we have to be really careful when we sort of go back to that very, very distant, misty time in which, Australopithecines were these 3.5-foot critters that were barely upright and doing an awful lot of climbing as well. But they were just trying to hold their own against leopards who would more often than not just simply seize them and, eat them in a tree and let the bones drop into a solution cavity deposit, which later became a cave. Well, back in their days, human culture, or pre-human culture, such as it was not much to look at, not much to behold. And my argument, or my counter argument, would be, in fact, that all of the sort of not software, but soft substrates that have evolved culturally have more than picked up the slack to buffer us against the very things you've talked about. I would argue to you that there was a brief period, I don't know how long it was necessarily. Unfortunately, a lot of soft tissue doesn't easily, fossilize. And artifacts are beyond 3.5 million years or so, and some simple cobblestones, which were just fractured by dropping them on the ground.
Right.
There's not much to go on. But I think what we can say is there was probably this window. It could have been a few 100,000 years. It could have been up to 800,000 to a million years, where, in fact, yes, you're absolutely right. We were fairly vulnerable. And there, but for the grace of dog, I'm going to take an official agnostic position and be dyslexic temporarily and say there, but for the grace of dog. Yes, it is Joycean, yes. Not quite stream of consciousness, but I'm getting there. Give me enough time. So my argument would be we sort of dodged that bullet. Now, it seems like an awful lot,
Well, of course we dodged that bullet.
Well, obviously, we're here. Yeah. But here's the thing. That's not an unusual story in evolution. It's just sort of happenstance. And you could sort of argue that, in effect, well, yeah, I mean, I'm not saying the universe favored us and shined its light down upon us and protected us, but we did somehow get through, and there were a number of bottlenecks to go through, of course. Populations probably crashed and all that stuff. But the bottom line is culture starting, gosh, who knows when, but probably something shy of 1 million years ago, culture finally sort of picked up the slack. And keep in mind too, once we were bipedal, we were very migratory and migrating very, very great distances that were unheard of in other non-human animals at the time.
So one of the issues here is that you're picking your data, and which is expected and
that happens.
Applauded, and it's good. Because if we don't start with the Australopithecines, but we start with Homo erectus and Homo habilis, which may be the same species for all I know, but you'd be the expert on that. Do you think it's the same species?
No, they're definitely genus Homo. They're a breakthrough. There's a breakthrough by at least Homo erectus. By Homo habilis is people have argued that it's essentially a very, very derived Australopithecine. But Homo erectus is definitely, they're there. They've arrived.
Okay, so by Homo erectus, I may be 4 feet tall, for example.
Oh, you're 5 feet, 5 to 5.5 feet tall. Yeah.
And I'm trying to get out of the forest.
Right.
Or at least I want to exploit the in-between area. And that is extremely dangerous because I'm good to eat.
But now,
for all kinds of predators.
Now I'll speculate, but now, and I don't have to really speculate too much because we have some amount of paleodemographic data on this. But now you're dealing with groups, social groups of a particular kind. And I would argue that sociality, but a particularly novel kind of sociality, picked up the slack way before we had some hyper-elaborated kinds of cultures to buffer us. So you've got people...
So if I'm going to exaggerate your point, people are nice to other people, and they protect each other. And that's what saved us.
Yeah,
no?
Well, not necessarily nice. I mean, they're not necessarily ultra. Maybe it's kind of you scratch my back, I'll scratch yours, or we're in on the hunt. We're going to do this together.
Sure.
But by Homo erectus, certainly we were not simply we weren't simply scavenging, although we might have done that, by happenstance. We may have done that opportunistically. We were hunting. And as soon as we're hunting, and we seem to be hunting socially, and we have tools to actually butcher animals a certain way. We're doing all this stuff. So arguably, there's some indirect evidence that we've got each other's back.
Yeah.
So let's kind of move. I think we've taken too much time in the
No.
distant past.
This is, everybody listening to this is asking themselves, if we're so nice and we're so cooperative, then how come we're so nasty?
Well, because we're all animals, and nastiness now has a label, but it didn't have a label before we had language.
Right. It had the label, I'm hungry, you look good to eat, and so
whatever.
on.
Yeah.
Right.
Well,
I've just read a book by Mircea Eliade, which is a classic, I understand, on the history of religion. It's called The History of Religion, but it's in fact an early history of human evolution, human biocultural evolution, right? And that covers 1 million years and more.
Sure.
And this particular view of humanity is quite nasty. It doesn't try to be nasty, but it kind of reluctantly.
I wouldn't say, I would say realistic, because I'm not trying to sort of put a nice sort of smiley face emoticon on all of this. This is not totally selfish altruism. Some people might argue this is group selection at work, whatever. I don't even care. I'm not even going to wade into the debate about group selection. But the idea is there's a benefit to me, so I'm going to act to do something for you or in favor of you to have your back. So sort of moving or segueing forward, and I'm trying to remember where we started, but the bottom line is, I think I'm very.
I would not call any of my robots nasty, just for the record.
Fair enough.
See, and that's a biological deficit from the viewpoint of evolution.
Just don't turn your back.
Benefit.
Don't turn your back.
There's a big red button on my robot.
Excellent. On-off switches are absolutely critical,
and there always will be, I might add.
Yes. Now, husband, if you interviewed husbands privately, they would say that of their wives. They would say, "Damn, why isn't there an on-off switch?" Wives would say the same thing about husbands, depending on. This is an age-old.
Now you're really making me uncomfortable.
I know. I'm sorry. Let's move right along. So I guess my argument, Bernie, you got my number. I'm a dyed-in-the-wool optimist, but I do think that we are entering upon a point at which we can reasonably talk about certainly intelligent artifacts, artifacts that issue forth, original, you might even argue highly creative acts that are novel, that are idiosyncratic. They're not necessarily 100% predictable, which is kind of cool, because that's a lot of what we observe in animal behavior, human behavior as well. So I have I guess I have a rosy perspective, but I think it's a realistic perspective. I think we're on the right track, and I'm not sure whether this will come to fruition in my lifetime, but I do very well see a path toward conscious artifacts, as my late father would call them, conscious artifacts. I think that there's a road. I can see the road.
Yeah, he actually wrote a road. It's in my office on the bulletin board.
Oh.
Yeah. I went to a meeting sometime in the 2000s, and I sat in on a machine consciousness workshop, and it was just dreadful. And it was just, and I came back and reported it. And your dad, Gerald Edelman, we had a build a brain group. And I said, here's what's going on in the world. And he was kind of appalled, like, that's just not how to study consciousness. That's not consciousness. He goes, I'll tell you what a conscious artifact should have. And then I wrote it down. I wish I had dated it. I have the rough date. I wrote it down in my lab notebook and saved that one page. There were a bunch of steps. I won't go through them that we need to take. We've done some of them: value systems, learning and memory, going to kindergarten, so having some sort of learning and development. One of the hard ones I just don't know how to touch is natural language. There are systems, right, that are very good at language, but there's still a lot of issues, a lot of work. It's not natural. It doesn't have the feeling. It doesn't have the meaning behind the language.
Right.
And to get a conscious artifact, you have to have some sort of report, and the best way to have the report is language. But,
yeah, absolutely.
But that sits on my wall.
That's good.
Every once in a while, I show it to people. And then I had left, but they started the Conscious Artifact Project after I after I left, and people like, I think, Jason Fleischer.
Yes, that's right.
And Jeff McKinstry.
Absolutely.
We're
Eugene
looking
Ishkevich.
Eugene. We're looking at mental rotation and how you do things like that, and building that in systems.
So I think, not to make you blush. Unfortunately, this is an audio podcast, so you don't actually have to watch that happen. But I think Dad would be really proud. He'd be proud of you. He'd be proud that you have that up on your whiteboard or whatever. So let's bring this home, and I want to bring this home by asking you, Jeff. What do you think? Give us a sense, as briefly as you can, but don't hold back. How do you see the road ahead? What do you see happening, and what's a kind of a rough timeline for all of this?
That's a tough one. I think in the next 5 to 10 years, you're going to see more and more intelligent systems, and I don't think they're going to go the road of making a conscious system, but they're going to be like one-trick pony kind of things built, and people are looking at biology and how the brain does it, because they realize they've hit sort of an asymptote with this next wave of AI. So when you talk to people on the street or at the agencies, they are starting to look back to the brain science and neuroscientists and ask them, how do you do these things so we can get over certain things like transfer learning or catastrophic forgetting or lifelong learning is a big government project. So these things are going to come out. You'll see them in your smartphones, I bet, in your maybe self-driving cars, a bunch of other things, assistants. If you get out beyond that, I think like you talked about with the energy efficiency, you're going to see a lot more exploration, and we can't get to some of these places we want to explore with humans. So you're going to have to see a lot more intelligent systems that are really energy efficient.
Right.
That's going to be happening probably in the next 20, 30 years.
Cool.
Yeah.
So, Bernie, what do you see as what do you see in the way of the future of all of this? What's your view of all of this? Do you see conscious artifacts in your lifetime? Do you see conscious artifacts at all happening at all?
I'm a skeptic on everything, including, I used to be a skeptic on biological consciousness outside of humans. And I'm no longer a skeptic, so I do have the capacity to learn. I really don't know, and I actually feel rather worried when people essentially take very dumb systems, which has been going on for quite a long time, and started off in the 1970s or 80s, I think, with a system called Parry, the paranoid patient. And you may remember Parry. It was very trivial. It consisted of just a list of questions and answers. And the argument from the psychiatrists who organized this was that paranoid patients, when they get suspicious of the therapist, really are very simple because they're so suspicious, right? You ask them a question, how's your day? And they wonder if you're trying to embarrass them or shame them or make them feel bad. So this was a trivial system that fooled medical students who had just learned about paranoid schizophrenia the week before, and now they had a chance to work on these computer terminals and interact with what they thought was a human being.
And they were snookered.
They were snookered.
Yeah.
And human beings, we play with dolls as children.
Sure. But
we project, project human features onto the night sky.
Oh, sure. But let me.
But you're talking about the Turing test, basically, right?
Yeah, it's
in
similar.
a way.
Yeah, what is called the Turing test, which is not really.
Yeah,
but
but there are these chatbots and that you see in this contest to actually pass the Turing test, and they haven't come close.
Well, they did
sometimes
with the paranoid.
Sometimes they fool you, but if you really probe them,
but
realize
the thing about it,
there's nothing there. Yeah.
I guess I would say now, fast forwarding to the present, I don't think anybody would I don't think most people would sort of take this too seriously anymore. They've moved beyond, in a sense. I mean, the general public, let me just, be careful here, because the general public is often taken in by these sorts of things. I think of Kismet, I think of MIT, the MIT Media Lab's efforts to sort of do what they might have referred to, some of them referred to explicitly as emulating emotional states and robots. And it was kind of cringeworthy. And so let's just sort of leave that aside, because to be honest with you, I think that stuff is, if it hasn't eclipsed already, it's on its way. Let's just end on the idea of what neural nets were. Neural networks were they were sort of the sophisticated end of something that you're talking about. They were sort of, they used the phrase neural, of course, but back in the day, they didn't really even halfway resemble real neural networks. But now, as Jeff intimated,
it's interesting. It's an interesting time. So when I was in grad school, I studied neural networks, and they were very small and simple.
Mm-hmm.
But if you look at the things that we call neural networks today, they're roughly the same thing. It's just there's two things that have happened. We have better computers, so they can have more and more layers, and we have more data. So that was the other thing. We need to train them. But I think we're realizing that they're not acting or doing anything that's brain-like or cognitive-like or conscious-like. And there's another field which I moved into, which was based on neurodarwinism, which was you want a selectionist system, you want the architecture the brain has, because the anatomy is so important. So you don't want these feed-forward networks. Right. And so we were building, and we are still building, systems that have anatomy, that have the dynamics that actually real brains do.
So not to put too much onus on Jeff, but to close, I would say that you're kind of the great white hope in a certain sense, or you and this group and also this community that we've discussed are kind of the, not necessarily the last best hope, but the hope for moving into a time when, in fact, we are doing simply something more than just trying to simulate, that these things are behaving in the world, they're acting in the world, and we can even look at their nervous systems doing stuff that reminds us very much functionally of what's happening in real brains. And I think Jeff is on the right track. Jeff may be, to some extent, in the minority, but I think at this table, I think we can agree that the approach, the biologically based approach, perhaps mixed in with, sort of intercalating itself into, or perhaps subsuming or overruling more traditional neural network based approaches. That's my that's where my sense of hope comes from, I think.
Well, I share a lot of that, including the sense of surprise at how quickly things have gone. And I keep on coming back to the same question, which I'm sure both of you also do, which is, where do we introduce ethics and morality in this game?
And I think that's a really good question to end on, but I also think that that's a whole other podcast. So I think we're going to have to leave that aside.
I will say something about that, because I get asked that a lot of times when I talk to general audiences, and I'll give you my answer is as an engineer, I want to work around safe things. So, and I think most of my colleagues would. So we put in all sorts of safety measures so that we know that these things will operate within bounds. And I think you're right. There has to be a discussion, because as these things get more complicated, that you have to work harder to stay within those bounds. But as a community, I think that's what we're trying to do. I think for the most part, everyone is trying to be a good actor. And so I'm not as worried about the ethics and moral issue as some people are.
So let's leave it there. Thanks so much, Jeff, for being here today.
Oh, my pleasure. It's been a lot of fun.
Appreciate it. It was great to catch up with you. And as always, thanks very much, Bernie, for hosting us. We really appreciate it.
Thank you.
And that is it for this episode of On Consciousness.
Good.
I'm David Edelman with Jeff Krichmar and, of course, Bernie Baars.